Hello viewers, as you know that I have discussed about the Sommerfeld theory for the understanding of atomic structure, and today I am going to discuss about the Pauli's exclusion principle, Hund's rule, symmetrical distribution of charge, Aufbau principle, quantum number, probability distribution curve. Pauli's exclusion principle, this is an important generalization put forward by Wolfgang Pauli in 1925, which determined the maximum number of electrons that an energy level can accommodate. Pauli's exclusion principle states that it is impossible for any two electrons in a same atom to have all the four quantum numbers identical, and thus in the same atom any two electron may have three quantum numbers identical, but not the fourth must be different. This principle is very useful in determining the maximum number of electrons that can occur in any quantum group. These are the energy levels. Sub-energy levels are also there. K shell can hold only 2 electrons, L 8, M 18 and N 32. Likewise, for K shell, for instance, since N is equal to 1, L can have only one value is 0, and M can also have only one value with 0. Hence, M can either plus half or minus half. Thus, there are two combinations of the quantum number as shown over here. If N is equal to 1, L is equal to 0, M is equal to 0, Ms is equal to plus half. N is equal to 1, L is equal to 0, M is equal to 0, Ms value will be minus half. This shows that in the K shell there is only one subshell, L is equal to 0, and in this only two electrons of opposite spin can be accommodated as shown in the figure earlier too. For L shell, since N is equal to 2, L can have two values 0 and 1. M can have only one value for L is equal to 0 and three values for 1, that is 1, minus 1 and 0, or we can say that minus 1, 0, plus 1, and Ms can have two values like plus half and minus half. For each value of M, these possibilities would give rise to 8 combinations of the 4 quantum numbers, keeping in the view of this exclusion principle. Thus, the major energy level L shell can accommodate 8 electrons, 2 in the L is equal to 0 subshell, that is known as S subshell, and 6 in the L is equal to 1 subshell, that is P, 3 orbitals of the P. So, these 6 electrons will be accommodated in the P subshell. Similarly, it can be shown that the M shell can have 18 electrons, where 2 in the L is equal to 0 subshell S orbital, 6 in the L is equal to 1, that is P orbital subshells, and 10 in the L is equal to 2 D subshell orbital, that will be called D orbitals, and so on. In this way, Pauli's exclusion principle, this table will show you the principal energy shell like this 1 and subshells 0 and orbital M and number of electrons in subshell and principal energy can be expressed in this way, that principal energy shell, if it is value 1, then the subshell value will be first 1s subshell, and the orbital M will contain only 0, and subshell number of electron will be accommodated 2 and the principal energy shell will be comprising of 2 electrons. But if the principal energy shell 2 value will be 2, then the subcell is equal to 0, then it will contain 2s subcell and 2p subcells, where the orbitals will be 1 orbital, m is equal to 0, 1 orbital, and this will comprise of 3 orbital, of which -1, 0, +1. Thus, they can accommodate 6 electron, and the total of 8 electron will be accommodated in this if the value of this principal energy will be 2. Then in the same way, the principal energy shell value, if it is 3, then it will comprising, or it will can accommodate the 18 electron, where 2, 6 and 10 can be explained as I have discussed for earlier too. In the 3s subcell, the subcell 3s, 1 orbital will comprise of 2 electron, and in 3p subcell the 3 orbitals will comprise the 6 electron, keeping these things in view, that -1, 0 and 1 value of m orbital. Thus, in the same way, the 3 d orbital or the d orbital will comprising of the 5 lobes of the orbital, which can hold 10 electron, 2 in each, that is -2, -1, 0, +1, +2. These will be the 5 orbitals of the third subcell. In this way, it can accommodate 10, and the total in the principal energy shell, the total will be of 18. Now, if the principal energy shell value, if it is 4, then the subcell L 4s orbital will comprise of this 2 electrons only. The orbital m value will be 0 and the subcell will be 2. So, the 2 subcell number of electrons will be present in the 2, as I have discussed in the s orbital, and in the p orbital the 6, and in d orbital 10, and this will be the 4f orbital. This 4f orbital will comprise of the 7 orbitals like -3, -2, -1, 0, +1, +2, +3. Thus, these 7 combinations or 7 orbital will hold the 14 electrode, and in total the principal energy shell will comprise of 32 electrons. This is the pattern how these orbitals contain the energy level, or this is how these orbitals can hold the electrons in their sub energy levels. Now, I am going to discuss about the Hund's rule. The basis of the Hund's rule of maximum multiplicity, and would see how it can predict the most stable electronic arrangement of a given electronic configuration. According to the Pauli's exclusion principle, if 2 electrons have the same spin, that is the same ms quantum number, they would occupy different orbital, since they cannot have the same values of the n, l and m. On the other hand, if the 2 electrons have opposite spin, they can occupy the same orbital, that is they can have same value of n, l, m. In the case of the degenerate orbital, that is orbitals with the same energy, if 2 electrons are placed in the same orbital, electrostatic repulsion would be greater than when they are placed in different orbitals. Hence, for least repulsion, the electrons in degenerate orbital should be placed singly until it becomes necessary to place 2 of them in the same orbital, that is when the number of electrons exceeds the number of degenerate orbitals. Thus, the most stable arrangement is one in which there is maximum number of unpaired electrons. This is the first part of the Hund's rule. For illustration, let us find out the most stable electronic arrangement of a 2p configuration. It can be easily shown that there are 15 ways of arranging 2 electrons in the 3p orbital. These arrangements are as follows. Number 1, where the opposite spins of electrons are present in the one orbital. The spins are parallel to each other, but occupying the two different orbitals, and these are opposite spin but occupying the different orbitals. According to the first part of the Hund's rule is stated above, the arrangement first is least stable of the remaining two. Which one is more stable can be decided by involving the contribution of exchange energy. By advanced mathematical treatment, it can be shown that if on exchanging the position in space of two electrons with partial spins, there is no change in the electronic arrangement. It would lead to decrease in energy. Such a pair of electron called the exchange pair. The larger the number of exchange pair of electrons is termed as exchange energy. It would evidently carry a negative sign. As can be seen, there is one exchange pair of electron in arrangement 2, but none in the arrangement 3. The arrangement 2 associated with lower energy would thus be more stable than arrangement 3. Let us now consider the case of a 3p configuration. This configuration can give rise to 20 electronic arrangement, 3 of which are as follows. Like this, this fourth arrangement is giving you that the 2 electrons occupying the one orbital with opposite spin and 1 electron is in another orbit. Here in this fifth position, that is the 3 electrons, they are occupying the each orbital but with parallel spin, and in the sixth the 1 electron each occupying the orbitals, but 1 electron it is having the opposite spin and 2 electrons they are in the parallel spin. According to the first part of the Hund's rule, arrangement 4th is least stable. This fourth one is least stable. Arrangement 5 has 3 exchange planes of electron with 1 2 1 3 2 3, while arrangement 6 has only one such pair like 1 and 3. If E is the exchange energy, then the energy of arrangement 5 would decrease by 3E and that of the arrangement 6 would decrease by E. Thus, E of the 3 arrangements shown above, arrangement 5 associated with minimum energy is most stable. The electronic arrangement with maximum number of parallel electronic spins would be the most stable arrangement of a given configuration, since such an arrangement would have maximum number of exchange pair of electron and thus would have maximum energy. This is the second part of the Hund's rule. In order to understand the effect of symmetrical distribution of charge in orbitals on the stability of electronic arrangement, thus the shape of the various sets of orbital one by one will be discussed. The s orbital is spherical in shape, which implies that the electronic charge would be distributed uniformly in all directions, whether there is one or two electrons present in the orbital. These are the p orbitals, px, py and pz, where these dumbbell shape orbitals is shown. Of these three p orbitals, the orbital px is symmetrical, this is, and along the x axis, while the orbital py and pz are symmetrical along the y axis and z axis, like this. If we place an electron in px orbital, that is, we take into consideration px1 configuration, the electronic charge would be mainly concentrated in the x direction only. Likewise, in py configuration, the electronic charge would be mainly concentrated in the y direction. Similarly, in px2 and py1 configuration, the electronic charge would be mainly concentrated in the xy plane. Likewise, the electronic charge would be concentrated more along the x direction in the configuration px2, py1, pz1, and more in the plane xy in the configuration px2, py1, pz1. It is evident that in all the p configurations mentioned above, the charge is not evenly spread along all the directions. In other words, the distribution of charge is non-uniform or unsymmetrical. On the other hand, the distribution of charge in the configuration px1, py1 and pz1 and px2 and py2 and pz2 would be uniform or symmetrical in all directions. Configurations with an even or uniform or symmetrical distribution of charge in all directions would evidently be associated with lower energy and hence higher stability than the configuration with unsymmetrical distribution of electronic charge. A symmetrical distribution of electronic charge leads to a decrease in energy and hence an increase in the stability of the system. This is the d-orbital shape, where it is double dumbbell shape. It follows from the above discussion that of all the d configuration, the configuration dxy1, dyz, dxz1 and dx square y square and dz square, likewise the d2 xy and yz, dyz and dxz and dx square y square and dz square would have a uniform or symmetrical distribution of charge in space. Therefore, these configurations would be more stable than all other d configuration. It can thus be concluded that electronic arrangement exactly half filled or completely filled degenerate orbital would be more stable than any other electronic arrangement. According to the off-bow principle, the ground state of an atom, the orbital with a lower energy is filled up first before the filling of the orbital with a higher energy commences. In other words, the electron enters the various orbital in the order of increasing energy. The increasing order of energy of various orbital will be as follows. The orbitals will be filled first, then 2s, then 2p and like this and so on. In this way, the electron will be filled according to their increasing energy. This sequence of energy level can be easily remembered with the help of the pictorial presentation which I have shown to you, and this is the pictorial presentation of the filling of the orbitals according to increasing energy level. Actually, in Bohr's theory, quantum numbers were introduced as a matter, a necessity to fit the theory with experimental data. But in Schrödinger wave equation, such numbers come out in a natural way through mathematics in solving the equation. The numbers used to identify various states that are available to an electron are termed as quantum number. They specify the location and energy of an electron. Each electron is characterized by 4 quantum numbers: the principal, azimuthal, magnetic and spin quantum numbers. Each quantum number is associated with particular characteristics of electron, which is described as follows. The principal quantum number n, denoted by n. The principal quantum number defines an energy shell in an atom when one or more orbitals in the same energy may lie. The different orbits of same energy are grouped together as degenerate orbitals. These are the energy levels, as I told you earlier too, K, L, M, N energy. So, N is equal to 1, N is equal to 2 in the case of L, and N is equal to 3 in the case of M, and N is equal to 4 in the case of this energy level. Each energy level will comprising of the electron accordingly. It specifies the location and energy of an electron and is a measure of the effective volume of electron cloud. The shell corresponding to n is equal to 1, 2, 3, 4 are denoted by K, L, M, N respectively, as I have given to you earlier. Principal quantum number denoted by n, as the distance of the electron from the nucleus increases, its energy becomes higher and higher. This diagram also shows the structure of the orbitals: s orbital, p orbital, d orbital, and this is then f orbital, which is a diffused one. So, this is spherical in shape, this is dumbbell in shape, and this is double dumbbell in shape, and this is having a more diffused structure. Azimuthal or angular quantum number denoted by L. It determines the orbital angular momentum and the shape of the orbital, that is, whether the cloud is spherical, dumbbell shape, or some more complicated shape, as I have shown to you in the earlier pictorial presentation. It may have all the integral values from 0 to n minus 1, where n is the principal quantum number, each of which represent different energy sub levels or subshell. Usually the values L is equal to 0, 1, 2, 3 are represented by the letters S, P, D and F respectively. These letters actually are the initial letters of the words sharp, principal, diffuse and fundamental. Magnetic quantum number denoted by M. In a strong magnetic field, the lines of the spectrum of the atom are split up. This phenomenon is called Zeeman effect. There is also a splitting of a spectral line by an electric field, which is known as Stark effect. Thus, we get more lines in the spectrum of an atom in a magnetic or an electric field. This indicates that the energy levels are further subdivided by the field. Therefore, an additional quantum number is needed to specify this sub-energy level. This additional quantum number is known as magnetic quantum number. Magnetic quantum number m, denoted by n, it determines the direction of the orbital relative to the magnetic field in which it is placed. The various values of m for a given value of L are minus L plus 1, 0, 1, 2, L minus 1 plus L, or simply plus L to 0 to minus 1. When L is equal to 0, m has only one value, that is 0. It shows s orbital sub-energy level only. When L is equal to 1, m has 3 values of plus 1, 0 and minus 1. It indicates that it is the p orbital that has 3 different orientation, px, py and pz, as I have shown you in the diagram. When L is equal to 2, m has 5 values of plus 2, plus 1, 0, minus 1 and minus 2. It indicates that d orbital has 5 different orientation, dxy, dxz, dz square, dyz, dx square minus y square respectively. This table is showing the quantum numbers, orbitals and orientation. These are the quantum numbers. If it is having the value of 1, then it will have L value is 0, orbital will be 1, n value will be 0 and orientation will be s, and this spin will be plus minus half, and it will comprising of 2 electron. If n value has 2, then the L value 0, 1, orbitals will be 2s and 2p, m value will be 4s, 2, 4p, plus 1, 0 and minus 1. The orientation will be s, will be px, pz and py, and each will comprise plus minus half. Thus, the 6 electron and in total 8 electron. If n value will have 3, then L value will be 0, 1 and 2. The orbitals will be 3s, 3p and 3d. M value for s will be 0, for 3p will be plus 1, 0 and minus 1. For 3d, the m value will have plus 2, plus 1, 0, minus 1, minus 2. Orientation will be dxy, dyz, dz square, dyz, dx square minus y square, and this is the spin will comprising of plus minus half each, and total it will contain 10 electron. As a convention, clockwise spin is represented by an arrow pointing upwards, while anti-clockwise spin is represented by an arrow pointing downward. Hence, this quantum number is only 2 plus half and minus half according to the direction of a spin of the electron. Mathematically, this quantum number may be represented as mvr is equal to lambda upon pi under root s plus 1. Right side of the equation is spin angular momentum, where s is absolute magnitude of spin quantum number. In an atomic orbital, there is a probability of finding the electron in a particular region at a given radial distance and in a particular direction from the nucleus. This gives rise to two types of probability of finding the electron. Probability distribution curve. The radial probability distribution curve of electron. These curves give the probability of finding the electron at different radial distances r from the nucleus and are obtained by plotting the radial distribution function. From this equation, D is equal to 4 pi r square into r n I into r whole square is equal to 4 pi r square psi r square. Against the electron nuclear distance r, these curves for 1s, 2s, 3s, 2p, 3p and 3d electron in atom are shown in figure. These are the figures which are showing the probability or the distribution of the charge. In this way, you can see that the probability of the distribution of electron in the 1s is this way, while in the 2s it is giving you the curve that this is a little bit distribution, but more distribution will be from this distance to this distance. In the same way, we can explain these distribution curve likewise by showing their shape in the probability and distance values. From the curve for 1s electron, it is evident that the value of D is 0 at r is equal to 0. Now D increases as r increases from 0, passes through a maximum, that is peak, at r is equal to 0.53 angstrom, which is equal to the radius of the Bohr's first orbit r, and finally to 0 as r tends to infinity. Thus, for 1s electron, D is equal to 0 at r is equal to 0 and infinity. D is maximum at r is equal to 0.53 angstrom, makes a difference between Bohr's theory and wave mechanical treatment of the hydrogen atom. According to Bohr's theory, in hydrogen atom, the electron under ordinary condition, that is in ground state, always stays at a distance of 0.53 angstrom from nucleus, while according to wave mechanical treatment, the electron may exist at any distance from the nucleus, but the maximum probability of locating it lies at a distance of 0.53 angstrom from the nucleus. In other words, the radius of maximum probability of 1s electron is 0.53 angstrom. For 2s electron, the value of D is 0 at r is equal to 0. Now, as r increases from 2r1 and passes through second higher maximum at r is equal to phi into 0.53 angstrom is equal to phi r, and finally approaches 0 as r tends to infinity. Thus, for r s electron, D is equal to 0 at r is equal to 0, 2 into 0.53 angstrom is equal to 2r1 and infinity. In second, lower maximum lies at r is equal to 0.53 angstrom is equal to r. The higher maximum lies at r is equal to phi into 0.53 angstrom is equal to phi r. So, in this way we can say that the distribution of the electron density through these radial presentation can be understood. The variation of D with R for 2s electron as summarized in this diagram shows that there is a greater probability of finding the electron farther from the nucleus, higher maximum at r is equal to phi r1, but there is also some chance of finding the electron very close to the nucleus, lower maximum at r is equal to r1 at an intermediate distance is equal to 2r1. there is a surface at which the probability of finding the electron is 0, that is at r is equal to 2r1, d is equal to 0. Thus, the charge cloud represents of 2s electron consists of a sphere surrounded by second spherical shell. From this plot between psi square and r square and distance from the nucleus r can be seen that for 1s and 2s and 2p, it can be seen from this plot that maximum probability for 2p electron is slightly less than that for the 2s electron. Also, the small additional peak lower maximum for 2s electron indicates that 2s electron penetrates a little more closer to the nucleus than 2p. Hence, 2s electron is attracted more strongly by the nucleus than 2p electron. This, in other words, means that 2s electron is more stable than a 2p electron, that is 2s electron has lower energy than 2p electron, although both the electrons are of the same main energy level. Thus, I have given you the detailed account of the probability distribution curve and Hund's multiplicity rule, Pauli's exclusion principle. With these, you might have been able to understand about the atomic structure more precisely. Thank you.